Hey, Chung here. Um, so this time let's talk about um, another tree problem here. 270. 270 closest binary search tree value. Easy. I think it's pretty like standard easy problem. It shouldn't be too hard. Okay, let's take a look. So you're given a binary tree and a target is like a float number here, and you need to find out the node that is closest to this target, right? So in this case, we have 4, 2, 5, 3. The closest will be 4, right? So how do we do it, right? I mean, we can always traverse the whole tree, right? I mean, we no matter what traverse method we're using, in order, pre-order, post-order, doesn't really matter. We can just traverse everything, and then every time we see a node, we basically keep the current smallest distance with target, and then we just keep updating this node. In the end, once we traverse the entire tree, we just get the smallest one, right? Yeah, I mean that's kind of like a O(n) method, right? That's sort of the O(n) complexity n is the number of the tree here. But since remember here, so it's a binary search tree, right? It's a binary search tree, so the left side is always smaller than the right side, right? And we have target that can can tell us we don't have to do traverse the whole tree. We can just use the binary search tree to only traverse a certain level of the tree, right? How? It's pretty straightforward. So every time when we have a node here, we compare, right? Okay, so first we every time when we see a node, we like what we discussed for the first approach, we still keep maintaining that the minimum the minimum like distance with this target and that node, right? But when we do the traverse, we don't traverse to any node. We only traverse based on the comparison with this target, right? So if the current node is smaller than the target, right? Then we know we need to go to the right side, right? Because if even because the current one is already smaller than the target, it doesn't make sense to keep going to the left because we know all the left node will have an even smaller number than the current one, which will result in a bigger distance here, right? So if it's smaller than the current target, we go right. Uh, Same if it's bigger than the current target, we go left, right? And then once we finish traversing following that rule, we'll get the final result. Okay. Okay, let's see. Um, we're gonna have a helper function here to help us keep traversing the trees, right? Gonna be node here, right? And like I said, we're gonna have like a minimum distance here, like the system max size, right? And then we're gonna have like the results. Basically, the result will be the node number. We're gonna have set to 0, and then we return result, right? So every time, right? If first every always check the none for the node. If not node, so we just simply return, right? That's how we stop the traversing, right? For each of the leaf node. If right, if target dot value it's less than the node target value is less than the target, right? Then we traverse to the right. Okay, yeah. Like I said, for each node, we will be converting. I'm not going to use those fancy Python functions with the lambda functions. I'm just going to like do a simple if else here, if statement here, if abs, because we want to calculate the distance, right? So we want to do an absolute value here, and node dot value minus the target, right? Smaller, right? Than the one we have in the small distance, right? Right. Then we're just updating it, right? Minimum distance. And also update the result with the current node value, right? So basically that will be, we keep updating those two variables here, right? And then if the current node is smaller than the target, we know we need to traversing to the right side, right? Because in that case, we can get a bigger number, which is which will be going to be a possible number that will be more closer to the target, right? So no, helper node dot right, else, right? Similar thing, else helper node left, right? Basically here, that's how we do a binary search. But every time we cut we cut the we cut the traverse by half, right? Yeah, I think that's it, right? So let's just run it. I'm gonna let's just run it. Oh, jeez. All right. How can we not calling it first? Then what's the use of a method if we never call it, right? A helper function. Okay. Yes, the same thing here. Since we're defining a in method helper function, we have to do a non-local for the minimum distance and the result, right? So, okay, cool. So pass basically pretty straightforward. No, and with this method, since every time we're cutting this like the tree by half, so the time complexity will be improved from O n to O log n, right? Which will be so log n is also the height of this tree, right? So because that's going to be a O log n or equals to the height of the tree, right? Because every time we cut it in half. Uh, cool. Yeah. Let me know. Yeah. Thank you for watching the videos, guys. Let me know if you guys need have any comments or if you guys want me to do any other problems. Yeah. Basically, I'm doing all the trees problem now, so it's gonna. Yeah, I think we'll have like a few other tree videos along the way in the future. Yeah. Cool. Thank you, guys. Bye.